Hello, hello. Welcome to the meat of this chapter. This is section 19.5, dealing with what is called Gibbs free energy. We're now going to take everything we've learned about enthalpy, temperature, and entropy and put it all together. So let us get going here. We go. So our objectives for today, we're going to talk about enthalpy and entropy in terms of free energy. We're going to talk about the relationship of what's called delta G, and we're going to talk about delta G standard. So a lot of times when we have chemical reactions, they can be exothermic or endothermic. But a lot of times the endothermic processes, such as dissolving ammonium nitrate in water, do occur spontaneously. We know that in general, endothermic reactions do not tend to occur spontaneously, but sometimes they are. Okay, and the reason we know that is because it does become more disordered. As NH4NO3 dissolves in the water, it separates out into ions, making it more disordered. However, sometimes processes occur spontaneously, but they also have a decrease in the spontaneity, such as an exothermic reaction that forms sodium chloride from its elements. Sodium ions and chlorine ions react with each other so to form solid salt, and that is an exothermic reaction, but it becomes more ordered, so it's a decrease in spontaneity. So a spontaneous process which results in a decrease in the system's energy must be exothermic. It must be releasing energy. You can't have something that is endothermic and also causes a decrease in the entropy. So the two things that affect the spontaneity of a reaction are the enthalpy and the entropy. And we're going to combine those two things mathematically here in just a second. So this takes us to Gibbs free energy. If we use enthalpy, which we know is the letter H, and we use the letter S, entropy, there's a way to determine mathematically whether or not a reaction will proceed spontaneously or not. Willard Gibbs, who lived in the 1800s, proposed a new state function that combines enthalpy and entropy. And the Gibbs equation is that G, which is the Gibbs free energy, is equal to the enthalpy minus the temperature times the entropy. And then if we put those together, we know, first of all, we know that temperature, or T is temperature, must be measured in Kelvin. This equation right here is given on the AP chemistry exam sheet. So the change in the free energy is equal to the change in the enthalpy minus the temperature times the change in the entropy. Okay, that right there, that equation right there, is the meat of this chapter. Okay, now if temperature and pressure are constant, then the relationship between the sign of delta G and the spontaneity is this. If delta G is negative, so if we come back to that previous equation, if the value we find for delta G is a negative value, then the reaction is spontaneous in the forward direction. So we don't have to try to predict, okay, it's exothermic, but it's also not, it's also is becoming less random, so what should it be? You simply put the numbers into the equation, you use the temperature that's given to you, and you solve for delta G. If delta G is negative, the reaction is spontaneous. If delta G is equal to exactly 0, then the reaction is at equilibrium, and it's spontaneous in both directions. And if delta G is positive, the reaction in the forward direction is non-spontaneous. So when you have a positive delta G, the reaction is not spontaneous. Now what's important though, if the forward reaction is not spontaneous, then if delta G is positive, then the reverse reaction is spontaneous. Okay, so in any spontaneous process, the free energy must decrease, which gives you a change of delta G as a negative value. Okay, so here's just something that kind of shows that there. If delta G were equal to 0, then you'd be right at here. Notice the free energy as you go from reactants to products, that in a case that is spontaneous, the products have a lower free energy than the reactants do. So overall, the reaction would have a negative delta G. Here's something that just kind of shows that again, where you start with pure nitrogen and hydrogen. As that spontaneously goes in this direction, you have Q becoming greater to reach KEQ. If you have it coming the other way, if you start with pure NH3, but you basically get to a point where you're at equilibrium, where Q is equal to KEQ. And once you do that, then delta G is equal to 0. Okay, when KEQ is greater than Q, it means that we've got an excess of reactants. The reaction is going to proceed spontaneously in the forward direction to reach equilibrium. When Q is greater than KEQ, the reaction is certainly going to, Q must decrease to reach KEQ. Q must increase, to reach KEQ. No, Q must decrease, sorry. Q must decrease to reach KEQ, and therefore it will proceed in that reverse direction. And at equilibrium, we know that Q equals KEQ. Okay, just like with enthalpies, just like with entropies, you can also have standard free energies of formation, which are with that delta G with the little degree sign. And remember, with enthalpies of formation, when elements were in their standard state, the enthalpy of formation was 0. With entropies, that was not the case. But now back to delta G, like heats of formation, the free energies of elements in their standard states are 0. Okay, standard states, as we know, if it's a solid, it's just a solid or a liquid. If it's a gas, it has to be at 1 atmosphere of pressure. If it's a solution, it's got to be 1 molar. In general, it's pretty obvious, like H2 and things like that. When they're in their elemental form, they are set to 0 with delta G. Okay, and certainly these standard free energies are useful when you want to calculate delta G for chemical processes, when we use that same equation we use with delta H and with delta S, where you take the standard free energy of formation, take the coefficient from the balanced equation, multiply by it for the products, minus the standard free energy of formation of the reactants, also multiplied by the coefficient in the balanced equation. And then you get your value for delta G. And again, what does that value tell us? Whether you use the delta G equals delta H minus T delta S equation, or whether you use this equation here, delta G always, all the delta G tells you is whether a reaction proceeds spontaneously in the forward direction or in the reverse direction. And remember, if delta G is negative, it's going to react spontaneously in the forward direction. If delta G is positive, then it's going to proceed spontaneously in the reverse direction. Okay. Now the nice thing is when processes are not spontaneous, so when you find your value for delta G, and delta G is a positive value, what that tells you is it tells you how much work must be done for that process to occur in the forward direction. So whatever your value is for delta G when it's positive is also telling you how much work must be done for it to occur spontaneously in that forward direction. So what we can do is we can look up Appendix C. This will certainly be given to us on the AP exam. We've got this equation here where we would look up the values for each of these. When we look them up, we find that the standard free energy for PCl3 is negative 269.6. And there's 4 of them, so we multiply that by 4. Chlorine is in its elemental state, so it is 0. P4 is not the elemental state for phosphorus, so therefore it does have a value of 24.4. This reaction, as we can see, has a negative value associated with it. Just using that information right there, we know that this reaction does occur spontaneously in the forward direction because of the negative sign. Okay, here's a reaction. In this case, let's look at this reaction. This is propane reacting with oxygen to make carbon dioxide and water. We've got a delta H of negative 2,220. Okay, and these where the questions start to get a little bit. You just have to think about this equation where delta G equals delta H minus T delta S. And they want to know, would you expect delta G to be more negative or less negative than delta H? First of all, we have to think about this. Is this a spontaneous reaction? Absolutely. Anytime you just give it enough activation energy, and the propane will continue burning with oxygen to produce the carbon dioxide in the water. So what we have to think about here is, okay, what's actually happening here? We already know delta H. We don't know the temperature, but the temperature doesn't change, so that one we don't know. So that one's not going to play a factor. What's going to play a factor is delta S. Is delta S going to cause delta G to be less negative, or is it going to cause it to be more negative? Well, let's look at our equation. In our equation, we go from 6 gas molecules on the left-hand side, 1 propane and 5 oxygens, to 3 gas molecules on the right-hand side. So we're going from 6 gas molecules to 3 gas molecules. Is that becoming more ordered or less ordered? Okay, hopefully we can see that with less gas molecules, it's becoming more ordered. If it's becoming more ordered, then our value for delta S is going to be negative. If delta S is a negative value, that makes this whole part right here, the negative T delta S, the negative and the negative, makes this whole thing positive. If that whole thing is positive, if we're taking negative 2,220, and we're adding something to it, that is going to cause delta G to be less negative than delta H. So overall, and it doesn't matter what the actual values are, but we would expect delta G to be less negative than delta H because this whole part right here, this negative T delta S, is a positive value because of the negative sign, because it's becoming more ordered in that reaction. Okay, and then we can actually look that up. And this kind of just explains what we just talked about. You can look at that for a little bit if you want, but delta G should be less negative than delta H. Okay, and then looking it up, we find that delta G for the reaction is what we predicted. It is less negative. The other one was negative 2,220. The delta G for this reaction is actually negative 2,108. Certainly very spontaneous still, but not as, it causes it to be less spontaneous due to the entropy. Okay, and a lot of times that's a typical AP question where they'll give you information like this, and they'll say which one causes this to be more spontaneous, the delta H part or the delta S part. And so you have to think, okay, which of these two is causing delta G to become more negative? And certainly, if that were the question, delta H would be your answer. Delta H makes it much more spontaneous, certainly because delta S is a negative value. Delta S makes it less spontaneously. It certainly does not make it more spontaneous. Okay, and tomorrow when we talk about temperature, we will talk a little bit in more detail about how delta H and delta S and the temperature will affect delta G. So for now, that's your equation. Again, this one is given on the AP exam. It is a very, very important one to know how to use and manipulate. And we know the key to all of this free energy is that when delta G is negative, it's spontaneous. When it's positive, it's not spontaneous in the forward direction, but in the reverse direction it is. And if you get a delta G equal to 0, the process is at equilibrium. And then just like with enthalpy changes and entropy changes, you can use the standard free energies of formation, and you can solve for the standard free energy change for the reaction using the products minus the reactants. Okay, so take a look at these tonight. There's obviously quite a few of them, and we'll be looking over the rest of them tomorrow in class. Don't forget about 1B up here.